Katie? Of today's homework?
Yeah.
Which one?
It's C. It's on this note.
Part Roman numeral what?
It's the
Roman numeral 4, part C.
the one with with like the tertiary properties protection.
Oh, okay. So how would you prepare that? So if I have a benzene ring, I want to make this. So if I said, how would you synthesize that from a benzene ring? You would need all the steps to put the oxygen on the ring. So our first step would be to say, okay, take our benzene and convert that all the way over to the OH. Then the question becomes, how do we react that OH and make a tertiary butyl ether out of it? And the one thing we cannot do is that we couldn't deprotonate this with, let's say we react it with sodium in order to form an O-. What happens if I try and do this? I can't. Why not? So the Williamson ether synthesis is what we talked about on Monday, but Williamson ether synthesis would not work with a tertiary halide. Because if I tried to do that reaction, what would I end up with instead? I'd end up with an E2, so this would go by E2, and so that's not the way I would want to do it. But then that's okay, because I could then say, well, why don't I just go ahead and react my phenol with tertiary butyl chloride and do an SN1 mechanism instead of an SN2. And you might say, well, can we do that with the benzene ring? No. One thing we cannot take a phenol and eliminate the OH group to form a carbocation, because we've not formed carbocations directly on a double bond. So we can't do this. That we cannot do. But having the phenol be a nucleophile so that we would lose the chloride to form the tertiary butyl carbocation, and then the phenol would come in and add to it to form the ether. That would be okay. So we would end up with the H, we'd end up with the oxonium ion and then lose the H plus to form the ether. So that would work, but the Williamson ether synthesis would not. And when people have suggested, we'll just add H plus to the phenol, okay, but the water's not going anywhere because we haven't formed vanillic carbocations. They're not stable.
So would you form that carbocation by Friedel-Crafts?
You could, or we could just say it's an SN1 reaction, right? I mean, that chloride is eventually going to come off of there, and what it does, the phenol is going to attack the carbocation. Aisha?
Can you use the OH and then react with the sugar with alcohol to get the same thing?
Let's protonate the tertiary butyl alcohol and then have the phenol react. So if you're going to react, you could do this. You could take tertiary butyl alcohol and the phenol and add H plus to it, and that would then make the ether. But the mechanism of that would be that, again, if I protonate the OH, it's not going to leave. So I would have to take this, the tertiary butyl group would be the one that would become protonated. So we would end up with that oxonium ion, then the water would leave, so that I would end up with my tertiary butyl carbocation, and then just like before, that's when the phenol would come in and add. So you can do that, but you're going to protonate the non-aromatic alcohol, the non-phenol. So that would work too. And in theory, this mechanism would always work. Because even if this was a primary alcohol, when you protonate it, the phenol would come in and kick off the water in an SN2 reaction. So this one would always work. Williamson only with primaries and secondaries. But that's traditionally how you would make a phenyl ether, is using Williamson.
On the front page of that packet,
You just hold it up.
Roman numeral 4A. So, because we can't choose Markovnikov, on that one, would there be two products, or would the one product be two sterically hindered that are fluid form?
4A. So we want to take the triple bond and, oh, okay. No, I know what you're asking. So if we're going to add our borate ester to that triple bond, where's the hydrogen going to add? Where's the boron going to add? Now, let's broaden the Markovnikov rule out a little bit for this. We said that the boron always added to the carbon that was least sterically hindered. It's the way that this would work. So what I would do is I would say sterically hindered, not so sterically hindered, and so I would say that the major product of this reaction would be to have the boron, the borate ester added on the end carbon, on the terminal carbon, and then had the H. So to me, this would be the major product of the reaction, because the boron has to add to the least sterically hindered of the two groups. And by putting the phenyl group there, I've made that side sterically hindered and the methyl group isn't. Because you're correct. Markovnikov would say you would get 50-50, but we have to take it a step further with this, and it goes to the least substituted. Well, it does go to the least. It goes to the least hindered carbon.
Roman
6B. Which one? 6B. 6. Oh, yeah. They're both no reactions. So in those cases, what I've done is I've put the nitro groups in the meta position, and I'm saying, okay, react this with maybe something like hydroxide at 350 degrees Celsius. This is going to be a no reaction simply because the nitro groups aren't in the correct. Well, let me take this back because actually there's something not there. Where's my erase button? There's no 350 degrees there. It just says hydroxide, right? So at kind of room temperature conditions, this reaction wouldn't occur because the nitro groups aren't in the correct positions. In order to activate this ring, in order for this to be activated, we need ortho and para nitro groups, not meta. So in the meta case, they would not be activated. So yeah, if I wanted to raise this to 350 degrees, yes, I would get reaction, but not at room temperature. If this was an activated ring with the nitro on the ortho para positions, yes. So that was a no reaction. Would just substitute for the chlorine, and the mechanism would change, right? It would go through a benzyne. So if I raise that to 350 degrees, it would, if I did that reaction now at 350 degrees Celsius, my intermediate would be that would be the benzyne. And so I would get hydroxide adding to both sides, so I would end up with an OH here and then reform the benzene ring, and then adding to the right hand side. So I would get those two products, but it would go through the benzyne non-activated mechanism versus the activated mechanism of having the nitro groups ortho and para.
Continues activated versus deactivated.
So activated would mean that there are electron withdrawing groups at the ortho and para positions. This is nucleophilic aromatic substitution. So it's exactly the opposite. If I want to, here's my, whatever my leaving group is, if I want this to be activated, I need an electron withdrawing group at the ortho and an electron withdrawing group at the para positions. That makes this an activated ring. So it's exactly the opposite. I'm using electron withdrawing groups, which would normally be deactivating in electrophilic aromatic substitution. And if those groups aren't there, then the system is not activated. So if it's activated, the mechanism I showed on Monday, where basically your nucleophile comes in, and then this pair of electrons moves over there, and then it moves back and kicks off the leaving group. That's the activated mechanism. If it's unactivated, then it goes through the benzyne. And if you have substituents on the ring, you're going to get two different products. There's problems on the sheet where it just said, okay, let's take a chloride and let's react this with something like hydroxide at 350 degrees Celsius. The only product that you get from that reaction is substituting the Cl with the OH. because a lot of people showed me that they had those two products, and my point was there's only one product there. This only becomes two products if there's something else attached to the ring so that those OHs are in different positions. So that's just one product.
So if you just added NH2 minus NH3, does it still only give one product?
Yes. If it's only a mono-substituted ring. But if it's a di-substituted ring, then you're going to get the OH. You're going to get the OH meta and para. If that group starts out para to the leaving group. In this case, we would have gotten these two products over here, and they would be different because one's a 1-3-5 substitution, and the other one is 1-2-4.
The NH2 and NH3 reactions now have to occur at
They can't because if we're talking about doing a reaction with NH2 minus and NH3, that's NH3 liquid ammonia, and liquid ammonia is like minus 35 Celsius, and so this is one of these things where how would we make the NH2 minus? We would actually take sodium metal and, well, we wouldn't do sodium metal. We would do something like sodium hydride, dissolve sodium hydride in the liquid ammonia, and the hydride would deprotonate the ammonia to make the NH2 minus. So that one can't be done at high temperatures. So that the NH2 minus really can only be done on an activated ring. But this hydroxide, because it's sodium hydroxide, it could very easily be done at 350.
The third one, what would be the other method you could look at the other one?
So we could use Gatterman coke, we could use HCl, carbon monoxide, aluminum trichloride, copper chloride to do this. The other, if we didn't have that, how would we do this reaction? Did anybody have any methods? Anybody who didn't talk to me? So that way we can see how creative people were in their methods. Ashton?
I added a DR2 after DR3,
Okay.
and then added magnesium,
Okay.
and then I added chlorate acid for C-O-HCl.
You added an acid chloride? You did this?
I didn't add an OH, it was just an
Okay. So this is an H on the other side?
H. Yeah.
Okay. All right, and then what? Oh, that would be it. Okay. Anybody have a method different than that, Aisha? Okay. Okay. And that's it? Okay. Anybody else?
Use Suzuki. We got ER2 FEDR3, and then the Boron ester with R is HC double bond
How do you want this? How do you want the borate ester to look like?
HC double bond R,
HC double bonded to O, yeah.
and then with the boron ester.
I'd have to think about that one. Katie?
I would use from ALCW.
So you added ethyl chloride, aluminum trichloride. Okay.
And then the four.
Okay.
And, then H plus H2 PCC.
Okay. Anybody have anything else?
I would CH2Cl with ALCL3 and then PCC. Well, I didn't have the I just had it.
Oh. Yeah.
And then PCC.
All right. One of these I would say would be 15 points. 15 out of 15. I would say this one is 15 out of 15. Because what you're doing is you're putting an ethyl group on the ring. You're oxidizing it to a carboxylic acid with CaMNO4. You're reducing it down to a CH2OH, and then using PCC to oxidize a primary alcohol up to an aldehyde. So that one doesn't have any questionable steps. Some of the other ones have questionable steps. I'm not sure what I would give that, because that's kind of pushing the limits, I think, of. I think what I would say is, how are you going to make that? Right? And the only way to make that would be something like this. And that wouldn't even work. So I don't think Suzuki coupling is going to work in this case. For this one, let's see. So for this one, we are okay at the carboxylic acid, because you put the alkyl group on and oxidized it to a carboxylic acid. Then if you would have reduced it down to the alcohol and oxidized it back up to the aldehyde with something like PCC or Swern, you would be there. So you're halfway there. The issue with this one is, how stable is this? And I think you're going to see a slide where I did this, because that reagent isn't stable. As a matter of fact, in the Gatterman Coke, we're basically using that, but we're making it and then immediately reacting it. So the reagents that you cannot use, your Friedel Crafts, when you want to react something with AlCl3, your Friedel Crafts, you're limited on your creativity here. I mean, I've seen 25 years or 27 years of creativity in terms of people trying to do Friedel Crafts on all sorts of things. that will never work. So let me just tell you what will work. What will work is AlCl3 and any alkyl halide that is an alkyl group only. No extra functional groups. Unfortunately, that leaves this one out. It's fine if it's just an alkyl group, but once you put anything else in there, that's not going to work. Or AlCl3 plus an acid chloride, where this is an R group. Not an H, not an OH, but an R group. So as long as you're doing your Friedel-Crafts under those two circumstances, you're okay. Once you get creative and try and change that, you may or may not, well, you're most likely not going to be right. So the idea here was we needed to remember that we could put a carboxylic acid group on the ring and reduce it all the way down to the primary alcohol and then oxidize it back up with Smyrn, PCC, Des-Martin, all the way up to an aldehyde. Right, then what you would do is do CO2 and H plus H2O to then put the carboxylic acid on the ring, and then you would be basically like here on this synthesis. And then you could do the lithium aluminum hydride. If you did it with this and then you did it with these, yes. Basically, if you're any questionable steps or any absolutely completely wrong steps, so you just want to make sure, and there's no set correct answer because there's multiple ways to do some of these problems. But if you think of each reaction as a letter and the overall series of reactions as a word, you can't really misspell the word horribly. You could interchange a couple of letters and it sort of looks like the word. But if you completely give me something that doesn't make any sense, then that's not good. Meaning you could get all the steps in the wrong order, you would still get some points. But if you give me steps that won't work, that's not good.
So in the exam, would you ask us how many steps to write out?
No, I would just say do that. And if you want to take 30 steps, you could take 30 steps. Now, realize that the most direct method is going to have the shortest number of steps. The more steps you put on there, the more likely you are to make a mistake. And this isn't any kind of diving or gymnastics where there's difficulty points. Your job is to get from the beginning to the end correctly. And you'll see, if you look at the old exams, there's lots of these kinds of problems on there. Aaliyah?
Okay, so the one I dropped out, maybe if you don't have to use it, but the further reaction,
This one you didn't see.
the one that dropped out.
Well, this one right here you didn't see.
No, I didn't see.
This one is just unstable.
Okay.
So that one has been crossed out in the past. The other one that's been crossed out in the past is this. Trying to put a carboxylic acid group on the ring by using that set of reactions. That was the first one that I crossed out. So your Friedel-Crafts reactions have to be limited to alkyl groups. They can't be anything more creative than that. So if you're going to use an acid chloride, that's got to be an R group. It's got to be an alkyl group. because this one would be impossible to make.
Go over the basic and non-basic anyway.
Whether something's basic or not basic. Okay. So for basic and non-basic, what it means is you're looking at a nitrogen and you're determining whether or not the lone pair on the nitrogen is part of or not part of the aromatic ring system. And so here would be my first two examples of basic and non-basic nitrogens. So the question is, for this nitrogen, is this lone pair, is this part of the aromatic pi system? Right. So the aromatic system, this nitrogen is sp2 hybridized, and so it already has p electrons that are part of the pi system. So this lone pair is actually is in an sp2 hybrid orbital, and is outside the pi system. And if it's outside the pi system, it's available to bond an H+. So in this case, are these lone pairs part of the pi system? No. So that would make this nitrogen a basic nitrogen. What about for pyrrole? For the pyrrole, is this lone pair part of the pi system? Yes? So it's part of the pi system because now the nitrogen still becomes sp2, but now that p orbital contains those lone pairs, so that you could have 2, 4, 6 total pi electrons. So in this case, this lone pair is part of the pi system. And so therefore, if it's part of the pi system, it's not available to bond an H+. You could say, but couldn't the pi system bond an H+? No. Right? That's the whole thing about being aromatic. Benzene aromatic compounds do not react with acid because they're super stable. So an H+ won't break up the pi system. So in this case, this nitrogen then is not a basic nitrogen. So the basic and non-basic go with the question of whether the molecule is aromatic or not aromatic, but now we're drilling a little bit deeper into this, saying, okay, specifically for a nitrogen or for an oxygen, is there a lone pair of electrons that is not part of the pi system? If the answer is yes, that can bond an H+. Michael?
Is there ever an NH group that would be basic for heterocyclic?
That would be basic?
Yeah.
If the lone pair is not part of the pi system. So in other words, can I come up with one? Well, I could probably. How about that nitrogen? So in this case, that nitrogen, well, this is the first thing we got to do is answer the question: is this molecule aromatic, non-aromatic, anti-aromatic?
I would say it's aromatic, but only either the nitrogen or the oxygen is aromatic.
Then it can't be aromatic. It's all or nothing. You can't because what happens? First rule: all of the atoms in the ring have to be sp2. So first rule is if I make that sp2 and I make that oxygen sp2, that has to happen. Then the second step would be how many pi electrons. If this oxygen goes sp2, what happens to the lone pair? Becomes part of the pi system. If this nitrogen becomes sp2, it becomes part of the pi system. That gives me 8. 8 is anti-aromatic. And so for both of these atoms to be sp2 hybridized, the system would become anti-aromatic. The system is not going to choose, because remember, it had to choose to be sp2 for each one of those two atoms. If it chooses only one, then it's going to be non-aromatic. So in this case, if that system is non-aromatic, then that nitrogen, that lone pair, is not part of the pi system. The oxygen's electrons aren't part of the pi system. And it's got to be a complete pi system. It can't just be a little bit of a pi system. So in this case, this would be a basic nitrogen because this system isn't aromatic. But that's something we have to remember. If you have a choice, if the atom has a choice, the atom will not choose to become sp2 hybridized if that will be make the system anti-aromatic.
So let's say there was an example and it didn't have a nitrogen and just had like a carbon with two pairs of electrons and then like a negative sign. So those would both be, that would be considered like two pairs of electrons, right?
So the lone pair makes the carbon negative.
Okay, so
Yeah, so it's either a lone pair or it's a negative sign. If it's both, it just means that the lone pair makes that negative. So in this case, that's going to happen in something like this with cyclopentadienyl anion. And so that carbon having the lone pair is what makes it negatively charged. And then for that one, what would happen? So the carbon's electrons are the carbon's going to be sp2 hybridized. That's going to make those lone pairs go into the p orbital, and that's going to give you 6 pi electrons, which is going to make it aromatic. So that's an aromatic anion. Alex, you had your hand up. A general list of topics. Oh, good. This is a non-exhaustive list because I will not remember everything. So do not come on Friday and say this is not something that you said, because I'm telling you right now it's not an exhaustive list. So we're starting with Aromatic, we're starting with aromatic, non-aromatic, anti-aromatic. And then we're talking about electrophilic aromatic substitution. So as far as electrophilic aromatic substitution goes, could you add an E plus to the ring and write all the resonance structures for that? So that would be a mechanisms question. Then it was the electrophilic aromatic substitution reactions. So was this, we started with the simple stuff like nitro, bromo, adding a nitro group, adding a bromine or chlorine, adding a SO3H group, and then Friedel-Crafts alkylation and Friedel-Crafts acylation. And then we also had the reactions. Any reaction we can use to generate a carbocation, that carbocation will add to the ring. And then we had our side chain reactions. Like if you're going to brominate an alkyl benzene, you're going to brominate at the benzylic position. The benzylic position is special because that's where the plus charge usually ends up, or the radical ends up. We had our oxidation of alkyl benzenes. We had our Birch reduction to remove the aromaticity. We had our Friedel-Crafts acylation and our Wolff-Kishner and Clemenson reductions to make the straight-chained alkyl groups. And then I think after that it was just simply a question of adding different groups to the ring with one substituent, then two substituents. We had our diazonium salts, our diazonium salt reactions, and then our Heck and the Gatterman Coke, the Heck and Suzuki couplings. And then into our nucleophilic substitution. So I don't know if anybody's looked at the older exams to see what kind of mechanisms questions I've asked previously. I can guarantee you it's been like electrophilic aromatic substitution, adding an E plus to the ring, and I can also probably guarantee that in recent years it's been nucleophilic, doing a nucleophilic aromatic substitution, whether it was on an activated or unactivated ring. I'm not sure if there were other ones that were on there. Nicole? Probably not, because the problem is most of these have resonance structures, and if they have resonance structures, then there's just a ton of dotted lines, and I don't think we need to add any more with transition states. Aaliyah? For an exam 3 or an exam 4. Those are probably really old, because those exam 3s were in the week before the last week of classes. And the sad thing about multiple choice is once I write one of those tests, it becomes difficult to write the second one unless I collect them up and keep them super secret, which if they're on the web, they aren't super secret. So it won't be multiple choice. Maybe the 4th exam, but let's get through the 3rd exam before we get to the 4th exam. And that one was normally with aldehydes, ketones, carboxylic acids and stuff, and that's what we're starting with next week. So I guess that's a non-exhaustive list of stuff to know. Anything else? And yes, it's a lot of stuff. I mean, this is what happens when we get further and further into the year. So, what you're going to have to know your chart that you memorized last week. You're going to have to know that chart. You're going to have to know how to make your different electrophiles, what the combinations of reactions would be, and then you're going to have to know, is something an ortho-para-director, is it a meta-director? Anything that's not on the 10 group chart is going to either fit into it's an atom with a lone pair attached to the ring, which makes it ortho-para-directing because it looks like N or O, or it will fit into your X double bond Y group, which is deactivating. So the SO3H group, that is not on the chart, but it looks like this. And so therefore the SO3H group would be deactivating meta-director. Okay. I have your stuff up here if you want to come up and get this. Other than that, if you have any questions, email me, come see me. Otherwise, I will see you on Friday.